example. In this case, we are looking at the conformation of a side chain, a tyrosine residue in a protein. It doesn't matter what protein we are looking at here. And if you monitor the conformation of this side chain by monitoring the dihedral angle formed by these 4 atoms, these 4 golden atoms. This is a simulation of about 1,000 picoseconds. And you can see that for a long time, nothing happened. It is fluctuating around a value of about 120 degrees. Every now and then you have a peak here, stays there for a while, comes back. And then after, let's say, 900 picosecond, it goes to the other state, a different dihedral angle, and it stays there for the rest of this short simulation, 1 nanosecond only. If you repeat this simulation using a slightly different initial configuration, then you can see that it might flip at 400 picosecond in the second simulation. Do it again, it might not flip in 5 nanoseconds. So this is a very important aspect of molecular events, because the flip of this dihedral angle, these atoms don't know each other. They don't coordinate their motion in a sort of intelligent way. It's just a matter of having the right fluctuation of all atoms happening at the same time to give you what you interpret as flipping of this ring. Sometimes it happens fast during one simulation. Sometimes you have to wait for it to happen. It's a random process. It's a stochastic process. And that's why it's very important, like many other aspects in MD, that we always look at the average behavior, average time scale associated with such phenomena. Yeah, so that's a little, I don't want to confuse you. At this point, I will come back to this, but that's something that you need to keep in mind. If you run one simulation, you can see the actual transition here from this point to this point is not taking even 1 picosecond. This is very fast. But you have to wait for the right moment to see the transition. This is true for large-scale conformational changes of your protein, for transport of your substrate through the channel, for any phenomena that you're interested in. So I usually use myself as an example of a molecular event. So let's say you're interested in watching me how I exit the classroom here. And if you just watching me here in my local minimum, maybe for the next 5 years, I just keep going left and right, and you just observe really uninteresting fluctuation of me in this local basin. But then maybe every 5 years or after 5 years, then somehow all the fluctuations are in the right direction, taking me toward the exit door here. You watch me again, next century, maybe I do it immediately in the first week. Now, this is the stochastic behavior of the process. And of course, the transition also depends on the barrier that exists between the 2 states. That also determines the probability of me crossing this barrier and reaching that point. That's another important aspect to keep in mind. So this is a fairly sort of localized, small conformational change. You can actually really nicely observe this kind of conformational change in a few nanoseconds of simulation. But usually, the kind of molecular phenomena that in biology you are interested at least are much larger. And that's why usually we are not able to completely describe them and provide enough sampling for them. We will be using the protein ubiquitin. This is a fairly stable, sort of hardcore protein, but it's a very simple protein. It's a nice example for those of you who want to also get familiar with proteins and use protein simulations later. It's very useful. That's the example that you will be using in your tutorial. And one of the aspects that you can expect from simulations is to be able to describe its overall deviation from the original structure. We can use the collective variable RMSD, root mean square of deviation, of a select number of atoms. You can look at the backbone atoms. You can look at all heavy atoms. You can look at all atoms, depending on what you are interested, and monitor that in time. So you usually start with the crystal structure, which is fairly well-defined, and then you can see that as soon as you thermalize the system, you start having RMSDs for average size proteins of about 1 angstrom. And after that, depending on the stability of the structure, you might either converge to some small value, or if your protein is not stable and continues to deform or do large-scale conformational changes, you can see that the RMSD value continues to grow. So that's a very nice, quick way of looking at what is happening to your molecular system. Just look at all atoms in one collective variable and see if something fundamentally is changing. So this, we can nicely also, actually, there are examples in which you can map the fluctuation, the RMSD for individual residues on the protein structure and visualize that, nicely showing what are the hot regions of the protein, for example, and what are the cold regions where you don't have much fluctuation, usually in the core of the molecular system, which nicely actually matches what we know from NMR structure for this particular protein. NMR is usually done in solution in which you have fairly large conformational fluctuation. It's not in the crystal environment, so you can nicely capture this conformational flexibility in NMR measurements. And that's a nice way to compare your MD with. This is, again, the same thing that I talked about. You can look at RMSD value per residue. You can sort of provide them as a plot or map them on the protein. This is actually one of the examples that you will be working on. So depending on the molecular system that you're interested in, you have to identify what are the interesting regions and how to characterize them. So this is an example of a potassium channel, for example. We know from the crystal structure, from previous structural studies, that it is formed by a bundle of helices. They form the main body of the potassium channel, but then they have a very important region known as the selectivity filter, where the protein decides what ions can go through. Potassium can go through, but sodium ions should not be able to cross this region. So you can, for example, do the RMSD analysis that we talked about on the selectivity filter alone or on the protein itself. In the total protein, you can see what if something is happening to the protein or not, something interesting, or repeat the analysis on the selectivity filter. And that's actually a very good way of identifying interesting regions. For example, I'm not sure if that's the case. It seems that something is happening here in the selectivity filter, and of course then you have to go in and watch the simulation, visualize the result of simulation, and see what might be happening here. Is it just noise, random fluctuation, or is it something interesting, some interesting conformational changes happening?
So this CHARMm is usually embedded in the membrane, right?
This particular one, yes.
Yeah, and in simulation, you use some constraints to emulate the environment of this membrane, or does it include the membrane?
So this particular one is actually, we have explicit representation of lipid bilayer around the protein. So we have the naturally, what we consider the natural environment of the protein. We have the lipid bilayer here, we have water on both sides, and then we have periodic boundary condition that essentially keeps the system in a good shape. So I will talk about some of these terms later. But again, at this point, this is just an example highlighting or emphasizing the fact that when you run a simulation on a complicated molecular system, you need to have some specific questions. Otherwise, that would be sort of total RMSD of the protein is the only thing you have put in your paper. You have to have some questions in mind. Is there any particular property that you want to monitor? Is it, if you are interested in bulk properties, yes. But if you are working with proteins or more complex, mechanistically interesting molecular systems, you need to have some specific questions. And then looking at the RMSD of those regions, important regions, is a very fast way of looking at what is happening. So usually I have two prescriptions. When you do an MD, use this sort of kind of a standard collective ways of analyzing the system and see if you can identify interesting regions. Then go back and see what is happening to your molecule in those regions. Another way is just watching the system and see if you can, if your eyes and your visual part of the cortex is identifying something interesting in the molecular system. Then you have to go back and quantify that and make sure that your eyes are not tricking you. But actually visualizing complex systems is extremely important when you're working with these proteins. You know, it really, I mean, your visual cortex is extremely powerful in seeing thousands of things at the same time. So you can really nicely see something, and then when you see that, you have to prove that it's quantitatively also significant. So these two go hand in hand. If you just report this, I think this is fundamentally important problem happening in my MD simulation. Maybe, maybe not. So you have to show what it is. Or if you just put a picture showing that this phenylalanine flipped at one point in your simulation without really quantifying and showing the time series statistics of that behavior, it's also not very significant. So these two should go together. So fluctuations you can also actually compare to experiments. So usually in the crystal structure, although the temperature of the crystal structure is pretty low usually, but still you have some fluctuation that translate into the so-called B factor or beta factor. And you can compare the pattern of B factor to the RMSD that you get from your simulation. Your simulation is done at a higher temperature, but so you will have larger fluctuation in principle, but the profile should have a similar shape when you compare them. So again, I mean, these are the kind of analysis that you will be doing later today. Okay, so let's come back to this was just to motivate you, sort of what to expect from an MD simulation. What kind of, you see the fluctuation. If you're lucky and you run the simulations long enough, you see interesting transitions between major states, and that's really cool. But how we go about this, running the actual simulation, as I pointed out, so this is our fundamental equation here. We need to know the forces to be able to calculate the acceleration. We work with the potential energy function as a function of all the Cartesian coordinates usually. That's our potential energy function, and the derivative of this potential would give us the force. Okay, so then essentially we have for a system composed of n particles, if it's atomistic, if these are planets or whatever, so we need to have a 3n coupled second order differential equations that need to be solved and propagated during the MD simulation. Okay. So the rest is essentially, as I pointed out, you get the initial coordinate from somewhere. We will randomly assign initial velocities based on a Boltzmann distribution, sort of Maxwell-Boltzmann distribution, targeting the temperature that you want to simulate at. And then at that point, from that point on, you just propagate and repeat the same kind of calculations over and over using the time step that is appropriate for the system. There are ways of controlling the conditions of the simulation, for example, controlling the temperature, controlling the pressure. There are additional algorithms that come in and will be used that might actually affect the behavior and dynamics of the system you should be aware of. We will talk about some of them as well. So this is one example here. So Langevin Dynamics is a sort of very common way of treating the molecular system in biomolecular simulations at least. So far we have been talking about this part. We said if you know the total force coming from your force field, then you are able to calculate the acceleration acting on that particular atom. But in addition to these forces that come from your force field, and we consider them natural force field, you might have additional terms in your dynamics equation that introduce additional or affects the dynamics. These two terms usually come together. One of them essentially introduce the effect of friction of the system, of the environment. So this gamma is a parameter that you specify in your simulation configuration. And the larger the gamma, the higher the friction would be in your system. You damp the motion of atoms much stronger by increasing the gamma parameter. Since we are usually limited in the time scale that we can reach using these simulations, it's highly advisable to use as small as possible values for this coefficient. So you will see we will use a 0.5 in the example that you will use. So that will essentially introduce some friction. And in order to balance this, then we have also a random noise term in the equation that balances everything. So this is completely random, and that might be another source of stochasticity in your simulation. Usually not a major one, but that can actually change the trajectory, even if you start with completely identical initial configurations. So Langevin Dynamics, but actually that helps you to control the temperature very efficiently and to couple the system to any temperature that you want. You can even actually affect different parts of the system differently, like you want to have very cold membrane, or I should say very hot membrane that can give you more thermal fluctuation, and very cold protein, or the protein should be at the room temperature, for example. You can actually couple the system, components of the system differently. Okay, so let me actually now get, okay, so this should come later. So one sort of comment about the time scale, and as I pointed out, limited time scale is a major limitation in our business. The other one is the approximations that we include in the force field, describing the forces acting between atoms. And if, in order to give you an idea of where we stand with this major limitation, these are the time scales associated with different kinds of molecular phenomena. In MD simulations, in atomistic MD simulations, we are limited to a femtosecond time step. Anybody wants to guess why? Okay. So in atomistic simulations, do we have a chemist here? Physical chemist, physicist? Okay. So can you tell us a little bit about the vibration time scales associated with molecular vibrations? Do you remember the numbers?
Hydrogen bond is like only less than 1 femtosecond.
Yes, exactly.
And CC bond, heavier atoms, is around 1 femtosecond.
Exactly. So you want to describe the motion of a molecule, right? And now, so the way, if you look at the force field, and we will look at it, you will see that our force field essentially is based on the chemistry. We describe bonds and as springs, bond angles as springs, and dihedral angles using cosine functions. So we know from chemistry, we know from spectroscopy, that if you look at the vibration of bonds that involve hydrogens, these vibrations happen on a sort of period of about 10 femtoseconds. So in order to describe the vibration of this CH bond properly, you need to have at least 10 snapshots taken. Otherwise, you don't know. For example, if you take every 10 femtosecond a snapshot, you will see always this CH bond having the same bond length because it's vibrating exactly at the same frequency, right? So in order to describe this vibration properly, you need to take 10 snapshots. Another technical reason is that if your time steps are too long, then your simulation and the energy conservation and everything will be affected in your algorithm. But I don't want to discuss those two technical issues. Fundamentally, if I want to describe the fastest degrees of freedom of a molecular system, my time steps should be short enough to have enough sampling of those fastest vibrations. Because the fastest vibration of a molecular system that includes hydrogen is the bonds that involve hydrogens, then I'm limited to femtosecond time steps. And that's actually a fundamental issue because I have to recalculate all the forces every 1 femtosecond. So if you want to see what is happening in a nanosecond, you have to repeat this calculation 1,000,000 times. Going to microsecond 1,000,000,000 times, you have to recalculate the forces between all these atoms and see what is the total force on each atom and take the next time step. So that's actually a very, very important aspect here for atomistic simulations. And that's the motivation of going to, for example, coarse-grained type of representations, or removing the hydrogens. That's the first sort of level of coarse graining that you can do. Let's forget about these hydrogens. Maybe, I mean, in principle, every vibration is important because the total motion of the protein is determined by the sum of all these tiny vibrations here and there. But we can make an approximation. Let's forget about the hydrogens and slowly think about just the heavy atoms. There are force fields known as the united atom type, in which the hydrogen mass is included into this heavy atom. All these groups is represented. This group is represented, for example, by a single particle. So using those force fields, now you can take longer time steps. Instead of one, maybe you can take 2, 3, or 4. There are ways of constraining the bond distance between these, between hydrogens and the heavy atoms that carries them. If you constrain those bonds, don't allow them fluctuate too much, then you can take longer time steps because you don't worry about them anymore. So this is, again, I repeat, this is a very important major limitation here. It translates into our limited sampling, into our ability to describe large transition, structural transition between major states, and whatever we can do to help would be useful. But of course, you don't want to lose the natural and physically correct dynamics of the system. There is a compromise. So most of the biologically interesting phenomena actually happen on a microsecond or longer time scales usually, because they involve proteins. If you look at the size of the system and the nature of conformational change, these are usually very slow. And until recently, we have been really limited to sub-microsecond type of simulation in this area. And since a couple of years ago, we have been able to run microsecond simulations, not very routinely, but it became a possibility. And very recently, actually, for a very small protein, people have been able to run a millisecond simulation. But that's really an exception. So there is this David Shaw, who is a faculty member of Columbia University. One of his passions was to revolutionize MD simulations. So he's a hedge fund person, so he's a billionaire. He could fund his research from his own pocket. No need to write grants or whatever. So they started a company called David Shaw Research, D.E. Shaw Research. And they wrote their own MD code, and they built their own hardware that can only do MD, doesn't do anything else, but does MD fastest way possible. So after 5 years investment, they have been able to do millisecond simulation. But I think that's the only case for a protein, actually, that I know of. So most people are still around microsecond, 10 microsecond or so. But hopefully in the future, we will be able to run more millisecond simulations. Anyway, so that's a very important aspect. I don't know why I have this slide so many times. OK, no, sure. Now I remember. So let's actually now talk about the energy function. As I pointed out, in order to calculate the force, we need to have the energy function. And a lot of effort that goes into biomolecular simulation is really defining this set of rules. So let's see what we have there. Let's start with a bunch of atoms not connected to each other. That's a very simple case. If you know the initial positions and you know their initial velocities, or you assign their initial velocities randomly using some algorithm, then you will be able to, and if you have certain number of rules defining how they interact with each other, then you are all set to do your MD simulation. So the basic type of interaction between any atom in a molecular system is the so-called van der Waals interaction. It comes from the fact that if you bring two atoms too close to each other, they of course bump into each other, they start repelling each other. But at larger distances, because there is this induced dipole kind of interaction between the particles, they always attract each other. So you have a combination of attractive and repulsive forces between any pairs of atoms in your simulation system. This is called the van der Waals interaction. And you can describe this using different functional forms. A very common form of describing this interaction is the so-called Lennard-Jones, 12-6 Lennard-Jones interaction, or potential energy term. You have the epsilon here that determines the strength of interaction between these particles. And then you have the, these R values of R mean, which is the sum of the van der Waals radii of the two atoms. And the Rij here is the actual distance between the two. At very short distances, where your R mean is smaller than Rij, or Rij is smaller than R mean, I should say, then this term becomes dominant to the power of 12. And you have a very strong repulsion between the two atoms. At longer distances, this dies very fast. And this becomes dominant, and you will have attractive interaction at large distances between any pairs of atoms. This is a very, when you look at these numbers, and we will do that, this is a very weak kind of interaction, but it exists between any pairs of atoms. So it can add up very quickly to a very strong sort of kind of interaction between bulky side chains, for example, or molecules. So this is the case if your system is not charged. Now, of course, some atoms carry charges, partial charges, what we consider. Some of them are permanently charged, like ions. Some of them are polarized. So you will have some partial charges that we will include in our classical description. So in addition to this general type of non-bonded interaction, we will have another kind of non-bonded interaction coming from electrostatic interaction between these atoms. And that is described in the force field that we use using Coulomb type of potential here. So you have the charge on atom 1, charge on atom 2, divided by the distance between them, and a bunch of constants to get you the right unit, essentially. So we will have Coulomb interaction and van der Waals interaction. So these are the two non-bonded interactions that we have in our force field. Pretty important, and usually the most expensive part of the calculation, because the number of these interactions is, in principle, n squared divided by. So this is pretty expensive, and that's why many people have tried to approximate some of these, especially the electrostatic term here, to make the simulations faster by introducing cutoff, by using algorithms like particle mesh evolve and other tricks. Okay, so as I pointed out, so this would be your non-bonded part of the potential, the Coulomb electrostatic interaction, van der Waals, and of course the force would be the first derivative of this equation, which is very easy for the program to calculate for you. So now that would be very simple. We are done. If you don't have a molecule, if you have a box of argon, then we are done. We know everything. We are all set to start our simulation. What makes these things very complex is that in a molecule, now you have bonds, which means essentially, as far as we are concerned, a different mode of interaction between atoms that are way too close to each other. We cannot describe these kind of interaction between two bonded systems using the two potential energy terms that we described in the previous slide. They have a special kind of interaction. They have sharing of electrons. You have a chemical bond there, and they behave totally differently. We know this from vibrational spectroscopy, how these bonds change in time and how they vibrate is pretty well established and characterized using IR spectroscopy. So we try to use that information to be able to have a force field that gives us the same behavior and motion for this molecular system. That's really the idea. So now the difficulty becomes here, now I have to deal with a lot of additional information. So what is this atom that is connected to that? Is it a single bond? Is it a double bond? Is this oxygen connected to an sp2 carbon, or is it an sp3 carbon? Do I have polar hydrogens or non-polar hydrogens? So it becomes much more complex. How many bonds do I have here? How many bonded terms should I include in a potential energy function in order to be able to capture the essential motion of this molecule. That's really the difficult part. So you can imagine for each molecule that we want to simulate, we need to have a topology file in which all these bonds are defined. Every atom now needs to have a special atom name. We need to have atom type for it that defines the chemistry associated with that and how it interacts with other bonded atoms. So that's actually 90% of the files that you need to include in the of the information that you need to include or give to your MD engine is related to the topology and individual properties of these atoms. Okay, and then the force field essentially, let me jump to the next slide. So the force field, your force field, this is one example of a force field. You can have different terms included here. This part is the non-bonded part that we already discussed. That's your electrostatic, that's your van der Waals. And now we have the bonded part. These are the three major, there are additional terms that are included in different force fields. There are three major bonded terms that are almost always present. These are really the basic kind of bonded interactions that you need to have. All the bonds are described as harmonic potentials or springs. You have the equilibrium constant for that particular bond, and the force constant associated with that. That's the strongest or the fastest vibrating degree of freedom among bonded interactions. Angles are also described as springs. So you have the bending vibration described as a harmonic potential. You need to have equilibrium value for that as the force constant. Dihedral angles. Everybody knows what a dihedral angle is? No? Oh, okay. So dihedral angle, dihedral means two planes. So dihedral is an angle between two planes. The first plane is formed by the first three atoms. For example, if you look at 4 consecutive atoms, the first plane would be the plane formed by the first 3 atoms, and the second one would be the plane formed by the last 3 atoms. So that essentially describes the rotational degree of freedom of a bond. You can have proper dihedrals, which are like this, or you can have improper dihedral angles, for example, for atoms that are in the center of sort of 3 other atoms. So those degrees of freedom, because you can imagine a bond can only stretch and vibrate, but the dihedral angle, you can have full rotation in a molecular system. So you need to have a potential energy function that, potential term that allows that, and that's why we are using a periodic term here, a cosine function. So we need to have a force constant that determines how easy it is for that dihedral angle or for those rotational degree of freedom to change. We need to have the periodicity of the system, how many times you hit the local minimum if you rotate this bond 360 degrees, and you need to have a phase determining the position of the minimum and maximum. But again, the point here, what I want to really communicate here is that, first of all, you have to introduce all the bonds in the system. You have to tell the engine. The engine doesn't know any chemistry. You have to tell me what is connected to what. How many bonds do I have? 5,500 bonds. Okay. For every one of them, I need to have a force constant. I need to have an equilibrium value. The same for angles, the same for dihedral angles. So after that, I will just go on, look at the position of the atoms, calculate the bond distance, actual bond distance for that bond, compare it to the equilibrium value, and get my energy or forces. So you have to introduce this all to the system. So that's what we discussed already. So bonds, bond angles, dihedrals. This is a proper dihedral angle. And this could be actually, dihedral angle could be also defined for a center. And this is called improper dihedral angle. That allows you actually, that helps you to, for example, enforce planarity of sp2 centers, or to actually keep it in a pyramid-like shape here. So by defining what kind of dihedral angle you are imposing there, you can keep its pyramidal shape, or you can maintain its planar conformation. So improper dihedral angle is actually something else that you will see in the force field that you will use today. Sort of graphically shown here nicely. These guys vibrate, bond angles and bonds, whereas a dihedral angle in principle should be able to rotate. So here actually another approximation, or for most of the kind of calculations that we do to here, you can see that this bond can stretch to infinity in principle, but it never breaks. Right? Because you have a harmonic potential, the energy just keeps going up and up, higher and higher. So that means in the classical description that we will have here, in contrast to what we had yesterday, no chemistry will take place here. No bonds form, no bonds break in this description. Unless you stop your simulation, you change your topology, you break a bond, you remove one of those bond definitions, and you continue the simulation. So there are some tricks of doing it actually in classical description, but for the most part, and especially for what we are doing today and tomorrow, no chemistry takes place. Okay, so this is just one example comparing three different bonds, a single bond, a double bond, and a triple bond. Again, as far as the simulation is concerned, the only thing that should be different for these guys is the force constant and the equilibrium value. I don't need to know what kind of specific hybridization is involved for these two carbons that are connected to each other. Just tell me how stiff that spring is. If it's a triple bond, it's a very stiff spring, 400 kilocalorie per mole per angstrom squared is the force constant, and the equilibrium value, B0, would be short, 1.2 angstrom. The double bond has a lower force constant and a longer bond distance, and a single bond would be even weaker force constant and a longer bond distance. That's the only thing that the program needs. So this is how we introduce single bonds, double bonds, and triple bonds. And the way we do it actually is by introducing atom types. For a single bond, the name that we give to this particular carbon would be different from this one, would be different from this one. So that's why we need the concept of atom names and atom types, and that goes into your topology and parameter file that you will work with. So I need you to remember these conventions here. So that results in different potential energy functions. I mean, as expected, a single bond would have a shallower potential energy shape here compared to a triple bond, and the position of the minimum is shifted to the left as you go from single bond to double bond to triple bond. This is, I mean, still 100 kilocalorie per mole per angstrom is pretty strong, stiff force constant. Actually, the bonded interactions are the highest frequency degrees of vibration, and you expect them to have the highest force constants. So these are usually on the order of 100 kilocalorie per mole per angstrom squared. Meaning that if you stretch or compress this bond by 1 angstrom, you will increase the energy of the system by 100 kilocalorie per mole. Pretty strong and stiff, very difficult to change. So bond angles are usually on the orders of tens of kilocalorie per mole if you look at the parameter file, and dihedral angles are the sort of softest degrees of freedom as far as bonded interactions are concerned. So here you are looking at the force constants that are on the order of a few kilocalorie per mole. Just to compare the shape of the potential energy that is introduced by this potential energy term, the force constant here determines the height of the barrier, how difficult it is to rotate. So as you decrease the K, of course, it becomes easier to rotate around that particular bond. I think the rotation of the methyl group shown here is described by the yellow curve here. I hope you can see it in the back. That has the lowest force constant, 2.5 kilocalorie per mole. The periodicity here, N, determines how many times you come up with the same configuration in a 2 pi rotation. For a methyl group, it would be 3, because after every 120 degrees, you reach the same position. And then the phase determines the position of the minimum. So for this case, they are all the same. The phase is for the, let me see actually. Yeah, for the case of the blue and yellow curve, we have the same phase. But it's a periodic function. You can actually really rotate freely a bond angle. Wow. I don't know what happened to this font. Oh, okay, it doesn't matter. So now let's take a look at the shape of the non-bonded terms. So here we are looking at the van der Waals interaction. This is distance versus energy. The depth of this potential energy well is determined by epsilon. By changing this, you can make it deeper or shallower. At short distances, you only have the repulsive term. They bump into each other, atoms bump into each other and repel each other very strong. But at longer distances, you see that you have only attraction between the two particles. So they both actually die very quickly. This is r to the minus 12 and r to the minus 6. Both of them die very, very fast. But the first term dies much, much faster. And that's why it doesn't exist after a certain distance. Because actually these are pretty short range, and they die very quickly with increasing the distance, they are considered short range type of interactions. And you can imagine that you can define a cutoff and say, you know what, it seems that after 5, 6, 10 angstrom, the interaction is completely negligible. Let's forget about them. Instead of calculating van der Waals interaction between all the pairs of atoms in my system, which might be 1 million atoms and cost a lot, I can make a reasonable approximation. I only look at atoms that are within 10 angstrom distance of the atom that I'm calculating a force on, and only calculate those interactions. So the cutoff has been actually pretty reasonably used for short-range non-bonded interactions. So in contrast, if you look at electrostatic interactions, now you are looking at Q1, Q2 over R, not R to the 6 or R to the 12. So they still die with distance, but at a much slower rate compared to van der Waals interactions. So that's why in these cases, the error that is introduced by cutting off electrostatic interactions will be much more significant compared to van der Waals interactions. So for this reason, electrostatic interactions have been actually, people have tried to come up with different ways of calculating these interactions without truncation. And for periodic system, there is a very efficient method known as particle mesh eval that essentially calculates the full electrostatic forces for you without truncation, but you need to have periodic system. You need to have periodic boundary condition for your system to be able to take advantage of this. This is a method that you will use. You can turn it on or off in your simulation configuration, and we will be using this for our example. That has been actually a method for electrostatic calculation, but then again, recently, I think people have been also trying to come up with similar ideas to calculate the Lennard-Jones parameters with less approximation. Okay, so before I go on, actually, I think this is becoming something important. This is one of the, again, I mean, after these 2 sessions, hopefully you get to know this method, you feel more comfortable of using it in your own research. But I would like you guys to also take a few important take-home messages from this course. So it's very useful to have better and more accurate descriptions of the potential energy, but we should not forget about the entropy part, right? So you are interested in the free energy change of the system when you're comparing the energy of 2 states. So you might spend a lot of time describing the potential energies as accurate as possible, but your method becomes so expensive that you have no description almost of the entropy, which is sometimes more important even. So there is always a compromise. In this particular case, for example, instead of using a cutoff of 10, I can have a cutoff of 100. My electrostatic interaction would be more accurate, but my simulation becomes more expensive, much more expensive, to the degree that instead of 100 nanosecond, I can only run 1 nanosecond simulation. And that's bad. So many people have been taking the other direction, making the potential as approximate as possible, going to coarse grain description, which is not even physical for a molecular system. We don't have any physics describing the interaction between two coarse grain beads. There is no spectroscopy, there is no number. But I go to this, how to call it, completely approximate method just to be able to run simulation longer, to deal with my entropy better. So there is always a compromise, and you should not forget about the importance of the entropy part. Good. So that's one thing that you need to remember. So I thought, I think after, let me see, when do you usually have coffee break? 10:30? Is that a good, or earlier? 10:30? Okay, good. So, so I talked about the velocity. So again, we want to start the simulation. We have an initial coordinates for the molecular system, but we also need a set of initial velocities. And this we can do very nicely based on Maxwell-Boltzmann distribution of atomic velocity that we know. It depends on the temperature. We know that actually in theory, if you look at the probability of having certain velocities in x, y, z direction, they follow the temperature here. So you can use this relationship to come up with a set of random velocities that we assign randomly to whatever number of atoms that we have in the molecular system. We just generate this distribution using an algorithm and randomly assign velocities to different atoms to get the temperature that we want the system to have. So at this point, you have the right temperature to the system, and sometimes you need to keep the system coupled to a thermostat or to a temperature bath until the system equilibrates, until you have really nice interconversion between potential energy and kinetic energy, and everything is nicely equilibrated. And if you look at the distribution of velocities at that point in your simulation, you can see that they nicely follow the theory. So here we are looking at the distribution of velocities along x, y, z. These are the colored plots, averaged, and compare them to what the theory is telling us. And you can see that there is a nice match between them. But the point is that actually we use this to assign initially, or later during the simulation, if you want to change the temperature of the system, if you want to reassign the velocities, we usually use this theory to assign the velocities to different atoms. That's the same thing, so you can also monitor the velocities to see what is the temperature of your simulation system, and that's actually how the simulation engine does it. So you get all the kinetic energy of the system, and then you know that for each degree of freedom, every atom takes half a kT, so you can calculate the temperature of the system very efficiently using this algorithm. Very nicely following a normal distribution in an equilibrated system. If your system is small, and that's another problem with molecular simulation, usually we have finite size systems, which means the fluctuations are going to be large. You will see if you measure the temperature of a bucket of water in the lab, you will have maybe, 25 degrees Celsius plus minus 0.2 in the lab. Whereas here you can easily have fluctuations of temperature that are 5, 6, 7 degrees because you have a finite system size and things fluctuate a lot. This is not only true for temperature, it's also true for pressure, for any property that you measure, any bulk property that you measure for the system. So what you measure in the lab for a sort of bucket of water is the average temperature of all these tiny bits in the system that are fluctuating wildly, but they average out each other. So at the end, you see a very, very sharp temperature, 0.1 degree fluctuation. Whereas when you come to a very small system, depending on the size of the system here, you might have really significant variation of the temperature that you monitor in your simulation system. So don't freak out if you see, oh, my temperature is now 6 degrees less than my target temperature. That's normal. If you increase the size of the system, the fluctuation becomes less, and you will have a sharper distribution. The same is true for pressure. In fact, actually, for pressure, sometimes things are really, really scary. They can really fluctuate a lot. Okay, a couple of sort of practical additional things that I think are important to discuss. As I pointed out, one major goal in this business, because time scale limitation is a major limitation here, people have tried a lot of different tricks to improve the time scale by increasing the speed of the calculations, by increasing the time steps. So these are some examples here. For example, you can introduce cutoffs. That's something we already discussed. Instead of calculating on all non-bonded interactions, you can only concentrate on a radius of 10 angstrom, 11 angstrom, 12 angstrom. The concept of PME I talked about. This is a way of calculating in an inexpensive manner, I forgot to mention. In an inexpensive manner, full electrostatic calculations, forces without truncation, but you need to have a periodic system. Sometimes, as I pointed out, you can consider bonds that have hydrogens in them as rigid bonds. Just ignore the vibration of the importance of the vibration of those bonds. And by doing that, you can go to 2 or 3 femtosecond time steps instead of 1. That already increases the time scale of your simulation by a factor of 2 or 3. You can actually decide to use a multiple time stepping. Certain interactions might actually fluctuate much more frequently, so you have to recalculate them every time step, whereas other parts of the interaction might not fluctuate as much, like your long-range interaction might not change a lot. Your PME type of interaction might not change a lot. So you don't have to recalculate those forces every time step. So these all become sort of, from a technical perspective, a little bit complicated, because every time you do this, any of these, then you are messing up with the original algorithm. You have to make sure that the energy is conserved. You're not introducing any error that is accumulating in the system. So from a technical sort of CS perspective, these are not trivial, but they have been worked out very nicely, and they have been working over the last decade or so. So we are pretty confident in using them. So let me see if there is anything else here. Yeah, so I think I covered. These are some of the tricks that are used. And I guess my next slide is introducing NAMD. So this might be actually a good time to have some questions and answer and have the break. And then once we come back, we can talk about NAMD and some real applications of MD, some examples to give you an idea of what to expect from MD simulations, et cetera, et cetera. So, questions. I usually say I would like to have 5 questions at least before we can go for the coffee break. Yes?
How accurately are you trying to solve the equations of motion? Like, did you use like a Relay algorithm, or would you use something way more accurate? Or?
As far as I know, actually, now you're asking me a question that goes way beyond. I know that we are using Verlet algorithm, as far, if I'm not mistaken. So, do you know? I think you know. I think you are using Verlet algorithm, but again, I don't know.
There are probably other algorithms like leapfrog.
Yeah.
But Verlet, velocity, and leapfrog.
Right.
Standard.
1. 4 more. Actually, that doesn't count because I really didn't answer that. Yes.
Probably in the previous slide, you were showing the variation of the temperature depends on the number of particles. And how does that relation is derived or?
So it's a normal distribution, right? did I do too much? So this is a normal distribution, and again, I mean, every particular atom is fluctuating, right? So now if you increase the number of these fluctuating particles, the larger the n, the probability of canceling each other, fluctuation becomes higher and higher. And that's why there is the sort of inverse relationship to n. Yes?
So usually in this simulation, we only include harmonic term. I mean, case x squared term.
I see.
I just don't know in real simulation or in real world, is it important to include maybe higher term?
Oh yeah, I see. Well, actually, in real world, I guess, I mean, you're talking about, if you're talking about unharmonicity,
yes,
that's actually definitely the case. But again, going back, I don't think we need to. So going back to the discussion I had, I mean, this is not harmonic. So you're talking about the harmonic potentials. Yeah, it is. I mean, we know from quantum chemistry and lots of spectroscopy that there are unharmonic contributions to the energy that describes the molecular system. But again, if you want to include those, your potential energy becomes more complicated and becomes more expensive to calculate. If you have a particular there is, for example, Morse potential that allows you to even break some bonds in classical description. You can do those things. You can make your potential energy much more complicated. But again, every time you do this, you lose speed. It costs you more. So if that is more important for your molecular system, rather than being able to sample it, that's what you should do. Exactly. I mean, but again, I mean, most of the approximations, I mean, the whole idea is around harmonic approximation. What you do when you calculate your frequency, even at the level of quantum mechanics, you ignore those unharmonic behaviors at this stage. And that's what we are doing here. So I should mention, actually, there are much more severe approximations here. So if you want to improve really the quality of the potential, there are much more important things. For example, polarizability that we need to deal with first before we go to those. But you're right. In real world, we have unharmonic behaviors, and they are not included in this simplified. Yeah.
Yes, I was going to just mention that even for these charges, you have only included per point, partial point charges.
Exactly.
You can also include maybe dipoles.
Absolutely.
Extend these
forces. Yeah, actually, that's actually, again, time scale is one major limitation here. The other major limitation is the force field, as you will see, as you're seeing. The questions are about, oh, this is not quite harmonic. It shouldn't be like a parabola. It should have a different shape. The charges are fixed. All the atoms in the molecular system that we simulate have a fixed charge. So like hydrogen has 0.4 electron charge on it, positive charge on it. So you can imagine if you bring an ion close to this hydrogen, it should become polarized. And you should have, for example, if it's a negative ion that you're bringing close to the hydrogen, you should attract or repel this electron, so you should have more positive charge on this hydrogen. You should be able to polarize the molecular system. But we don't have this. These are all fixed point charge approximation that we use in this classical description. And you can imagine that can have really significant ramifications of the dynamics of the system, on the structure, energetics, everything. So that's this kind of approximations going into a classical description that we are using here. Again, just to be facts. We know how to do it at a very high level of QM, quantum mechanics, right? But there is no way you can run the protein at this size using a quantum mechanical potential for an nanosecond. So if you want to see that, you have to sacrifice something or wait another couple of decades maybe. You can run everything quantum mechanics. I don't know. So there is that's another source, the approximations that go to the force field is another source of major, another major limitation of the description that we are using. Still, I don't want to end on this disappointing point, so I would like to point out that it seems that actually, at least in biology or in many other molecular systems, they are robust enough to still show reasonable behavior under the sort of not so optimal conditions that we use to describe them. You still see really meaningful behaviors when you compare them to experiments, when you try to describe how these proteins function, what kind of motions are involved. It still works, actually. Again, certain phenomena would be very sensitive to those approximations, and you should be aware of these approximations. If suddenly something doesn't work and you get a strange behavior in your molecular system, the first thing you should suspect is that maybe my force field is wrong. Could it be because I don't have polarizability? Could it be because I don't have unharmonicity? Just make sure it's not the case. You can even modify your force field to test. For example, let's say this hydrogen should be more positive in the presence of a negative charge. I know that. So I can artificially change the charge of that particular hydrogen and repeat my simulation and see if the phenomenon that I think I've discovered still is robust and is there. If that's the case, I say it's force field independent. What I see is real. It's a sort of intrinsic behavior of this molecular system. It's not because my charge is slightly wrong. So you can test these things very efficiently as well. Yes?
So there was a paper, I'm sorry, I can't remember who wrote it. This is about a year ago that I read it. That they found out a way, to measure solubility of some drug molecules pretty accurately, and they withheld the results, and they gave the molecules out to the MD simulation community. I don't know if you're familiar with this one.
No, I don't know the paper. That was done experimentally.
It was experimentally, and they said, "Here, guys, try to calculate the solubility." And people failed dramatically. I mean, it was a mess, right? And I think it probably was even worse than random, if that's possible.
I see.
So, and this is a follow-up paper where they compare like this. So, I don't know if you're surprised by that or not, but what do you think the community needs to do to fix that kind of performance? It seems like it's not predictive. We're not able to predictably do, say, biological molecules, even just something like solubility. What do you think needs to be done? Or is it the simulation methods? Is it the force fields? What?
Okay, so I mean, I am surprised by the last part that you said it was almost random. That part surprised me.
It was pretty bad.
Pretty bad, I'm not very surprised.
Yeah.
So because again, I mean, the quality of the force field,
Yeah.
especially for drug molecules, this is probably the most challenging part of our business because, I mean, so another thing that we will talk about probably tomorrow is that the way we put together things in the force field in a classical description is that we say, oh, this complicated molecule is composed of these 10 different components. We have a polymer composed of these residues. So instead of calculating the force field for the whole protein, we calculate the force field for these small molecules, these model compounds. And then we put them together and we assume that, okay, because we did a good job for those small molecules, this should translate in a reasonable behavior of the polymer. That's a sort of based on fragments, essentially. So fragments that have been used for biomolecular simulation for proteins, nucleic acids, lipid bilayers, they have been constantly refined further and further based on new experimental measurements. So they've been always trying to go back, instead of having the simple dihedral potential, for example, having the more complex dihedral potential that gives you the better behavior of the system. So these guys have been refined over many, many years. Whereas for drug molecules, almost every drug is a different species in a way. So we don't have that much experience with drug molecules, so it's very likely that we fail miserably. The force field is really, I would say the force field is the major source of problem. So for those cases, I would try to do maybe quantum mechanical type of calculations. I mean, this is going to be more expensive, but yeah, you can do free energy perturbation based on the quantum mechanical potential, or look at salvation energy and things of that sort for very complex systems that But again, in general, yeah, so you're right. This is, the first suspect is the force field, the quality of the force field that you have tried. So there are ways of improving the force field. People have been doing this. We are actually, our group is also involved in deriving certain properties, for example, charges a little bit differently, including polarization in the force field. I expect this to be a major step forward because that's a very real, strong effect, and we don't have it. So that hopefully changes things significantly. I still don't expect anything better than 1 or 2 kilocalories per mole. That would be great.
If you do density functional theory, you don't get 1 or 2 kilocal per mole anyway.
Yeah.
So I think they can, instead of using this classical empirical force fields, they can try and do some semi-empirical simulations to simulate a larger system. Actually, with the solvent and the solute and completely solubility is a little more, I would say, accurately. But then, they are also again parameterized. Models. They're not completely ab initio.
Yeah.
So they make, and of course you can treat larger systems because you're kind of throwing away all integrals and approximating them, like DFTB, density function, tight binding, or standard AM1, or some semi-ab initio, semi-empirical models. And some of those could give you better results. Because they actually have more chemistry included, more explicit. But yeah, if you are not satisfied, you can do full ab initio with models for solving. There are various kinds of models in that sense.
I think, if I'm not mistaken, I don't do much drug docking, that kind of. But you are talking about solvation energy, just in water, right?
Yeah, this is actually the paper here, but it's titled Solubility Challenge. Can you predict solubilities of 32 molecules using a database of 100 reliable measurements?
Okay.
And their conclusion was...
Who are the authors?
Antonio Linas, Jonathan Goodman, Robert Glenn. These guys are at Cambridge.
Okay. I see. But actually, no, I think that, again, because the diversity of the molecular systems are so broad in the case of drug molecules, I think that's probably in terms of free energy calculations and energetics, also that would be the most challenging for us. But again, the same problem existed with protein folding. If you look back many years ago, there was no way we could fold anything or we could predict any structure, but things have been improving a lot. And quite recently, there was a paper from the Shaw research that I mentioned, the millisecond simulation guys. They folded 12 different proteins. So we are still struggling with folding a single protein. These are very small proteins, but still. They folded 12 proteins, not only once, they ran the simulation long enough to see unfolding, refolding, unfolding, refolding, pathway, kinetics. Many people suspected that with this approximate descriptions, you accumulate errors if you go beyond microsecond, reaching millisecond or behavior. But I guess this paper sort of proved that no, there is hope that we can actually get the right behavior. So yeah, so definitely you will see much more improvement in the quality of the force field. That is one of the major sort of shortcomings. So you guys should always remember. Okay, I'm going to count that as 2. That was a very nice question. So we can unless there is more questions. Good.